Check. Yes. Sorry, I got disconnected. Now also the connection is not very good, but it works. It is working. Yes. So what we were discussing, I'll have to share the screen again, I think. Yeah. Yes. So what we have here is we convert the value of the variable we are looking at into its z value. Yeah, z value is essentially distance from the mean. Z value, I'll try to write it. Yeah. So z value is the distance of the given value of variable from its mean, from the dataset's mean, in terms of its standard deviation. Yeah. So even if you look at the formula of the z value, it is clear. So z value is telling us how far a given value is from the mean in terms of standard deviation. That is how many standard deviation away from the mean the given value is. Yeah. So once we find out, then we come to this z table or normal distribution table. We look up the value of z in the leftmost column, yeah, up till 1 decimal place. Yeah, so we locate that. Say, suppose z value of a variable, yes, we are trying to study what is the probability of finding out that value of the variable, and the z value of that variable comes to 1.75. So we will see 1.7 in the first column, and for 5, the 5 in the second decimal place, we will see the row under 0.05 column. So 1.7 here and this 5. Yeah, 0.05 under the value under 0.05 in the row 1.7. So the value is 0.4505. You can see in this table 0.4505. Yeah. So in the exam you will get the normal distribution table as well. Yeah. So you can easily use that. Yes.
How you calculate the 1.75?
Yeah. If say suppose z value is 1.7. Yeah. So 1.7 we see in this leftmost part. Okay, but yeah, there is something like a laser point also, but
you can just try with the right click and find out the pointer.
Right click. Move here. No, cancel. Copy here. Yeah. So the cursor is visible?
Yeah.
Yes, so 1.7 in the first column and the second decimal place of 5. Yeah, we are looking at Z value 1.75. So 1.7 in the first column and point. So 1.75 Z will cover the area of 0.4599. What is in the body of this table are the areas or the probabilities. So if some value is 1.75 standard deviations away from its mean, then the probability of getting a value between mean and that value is 0.4599. I'm not sure how much of it is clear. Yeah. So let me again try to draw these things. Yeah. So suppose we are measuring heights. This is the probability distribution of heights. On the x-axis, there are all heights. And as this data is normally distributed, yeah, it is like this. It is a normal distribution curve. So at the center of the curve on the y-axis will be the mean. Is the mean. Say it is 5 feet 8 inches. Yeah, is the mean. We can typically, when in normal distribution curve is drawn, we also draw this line joining the peak and the mean. Yeah. On y-axis, what is there on y-axis? It is the probability. Probabilities. Yeah. So this is the heights. Here will be other values of heights lower than the mean. On the right side, there will be values higher than the mean. Yeah. Suppose the mean is 6, the standard deviation is 6 inches. It is a data, so the data will have some standard deviation, some mean. So the value of standard deviation of this data set for which we are drawing this curve, yeah, suppose it is 6 inches. So what is the probability of getting a value, say from 5 feet 8 inches to 6 feet? Yeah, suppose this is 6 feet here. What is the probability of getting a value in this range from mean to 6 feet? So what we will do, we have this value of variable 6 feet. We will convert that into its z value. So z value of 6 feet will be 6 feet minus 5 feet 8 inches. You can write feet here. 6 feet minus 5 feet 8 inches divided by 6 inches. You can actually, yeah, remove the units if you can keep that in mind. Yeah. So 6 feet minus 5 feet 8 inches will be how much?
0.2.
Yeah, it's 4 inches, right?
Yeah, 4
inches. And in the denominator, it is 6 inches. So 4 by 6 will be how much?
2 by 3, that means 0.66 something like that.
Yeah, 0.66. Yes. So the Z value for 6 feet in our case in this situation is 0.66. So what is the probability of getting from getting a height? What is the probability of a person's height being between 5 feet 8 inches to 6 feet? Or in other words, what percentage of people in the data set have heights between 5 feet 8 inches to 6 feet? For that, we will look at the Z table. Yeah. So 0.66. Value is 0.66. So 0.6 we will see in the first column. 0.6. Yeah. Okay. The power is back. Very nice. Yeah. So in the first column 0.6, and for the second decimal place, we will move in the same row and come to here 0.2454. Yeah. So the probability of getting a value between 5 feet 8 inches to 6 feet is 8 inches to 6 feet equal to 0.2454. Yeah. So this is the application of normal distribution. That means the area under the curve, this area under the curve, this much area is 0.2454. Yeah. Or 24% of the area is under the curve. So there is 24% chances that the height will be between 5 feet 8 inches to 6 feet. Or you can also say 24% people will have height between 5 feet 8 inches to 6 feet. Yeah. So similarly, we can try to calculate area under any part of the curve. Yeah. Area under any part of the curve. So there can be different situations like that. So in this case, given all the data same, what is the probability of getting, say, 5 feet, the height between 5 feet, say this is 5 feet, that is 5 feet 0 inches to 5 feet 8 inches. What you will do? Probability of, I can change the color, probability of 5 feet to 5 feet 8 inches.
We have to calculate Z first.
Sorry?
We have to calculate Z value first.
Z value. Z value of what? Z value of 5 feet.
5 feet.
Yeah. Right. Yes. So Z value of 5 feet will be how much? 5 feet minus 5 feet 8 inches. Yeah. Divided by the standard deviation, that is 6 inches. So this becomes how much? 8 inches. Minus 8 inches actually. Minus 8 inches. Yes. And divided by 6 inches. Yeah. So that becomes how much? Minus 1.3.
Yeah.
Yes, minus 1.3. So Z value in this case is minus 1.3. So what is the area under curve? Yeah, what is this area? Yeah. Between 5 feet to 5 feet 8 inches. What is this area? Shaded in green. So again, we will look at the Z value. So now remember that the graph is symmetrical with respect to the mean. Yeah. Right. So the amount of area which will be a given z value to the right will be same as the given z value to the left. That is
Right.
the area between A's. So the area between mean and plus 1.33 will be same as the area between mean from the mean. So we can ignore the negative sign and see how much area is there between mean and z value 1.33. So 1.3 we will see in the first column, z column. Then we will move in the same row till we get to the second decimal place, which is 0.03. Yeah, so this is the probability value, 0.4082. 0.4082. Yeah. So this probability is 0.4082 or 40%, you can say. Yes. So similarly, given any value of the variable, you can find out what is the probability of getting a value in a given range, between that value to mean, between that value to another value. So it's not necessary that every time you'll have to stop at mean. Of course, mean will be involved. What I'm saying is you can also find out what is the probability of getting between 5 feet to 6 feet. Yeah, between 5 feet to 6 feet. So in that case, you will have to do this process twice. Once mean to 5 feet and second time mean to 6 feet. Yeah. We'll have to do the same process, find out z value of 5 feet, then what is the area between 5 feet and
Why
the mean.
2 times we have to do it, sir?
Yeah, because this is what we have done in the last two examples. What we did is find out the probability of getting a value between mean, that is 5 feet 8 inches to 6 feet.
Right.
That we did here.
But we have done only one time the z value, not 2 times.
Only one time, because it was just from the mean, from the mean to that value.
Yeah.
Now we have from another value 5 feet from here till here.
Okay.
Yeah. So we do that in two parts.
Yeah.
We
So
break
5
it
feet
at
to 5.8 and then 5.8 to that. Yeah.
6 feet. Yes.
Yeah.
So two times we'll have to do the whole procedure. Then the two different probability we will get, we will have to add that. In this case, this probability we got for this, and this probability we got for this area. So if we want to find out the probability of getting 5 feet to 6 feet all the way till 6 feet, so that will be 5 feet to 6 feet will be equal to this 0.4082, that is this value, plus 0.2454. Yeah, if we simply try to add that, it will be 6, 14, 5 and 6. 0.6536 or around 65%. Yeah. So in that way, yes. So in that way, given the data is normally distributed, we can find the probability of any such range, probability of getting a value of the variable in any range. Yes. So following this process. Now, what will be the probability of getting a value above 6 feet? Above 6 feet. This area. How will we find that?
So about we can minus 1 minus because the total curve is 1.
Yes.
Yeah.
Yes.
1 minus the remaining part, then that will be the above 6 feet.
1 minus the probability of getting a value below 6 feet,
Right.
will give us the probability of getting a value above 6 feet. So below 6 feet, what we will have to do, again, we will take it at the mean. So from 6 feet to mean, what is the probability? Yeah, we'll have to find out that. Again, we will get this value. And from mean to all the left portion will be 0.5. Yeah.
Right.
From mean to the whole left part will be 0.5.
Yeah.
So what we will do, yes. So the probability of getting above 6 feet, so we will add this probability to 0.5. So it becomes 4, 5, 4, 7. Yeah. Probability of greater than 6 feet. So in this way, we have covered all the possibilities, almost all the possibilities of finding out probabilities in a given range, given the data is normally distributed. Now coming to something called as hypothesis testing, in which we extensively use this normal distribution concept. Yeah. So let me explain the situation. Yeah. So now, suppose there is a treatment, yeah, a vaccine. Yeah. So from past data, we have 1,000 patients past data. So this will be little plain. So let me take another example, not vaccine, but rainfall. We are badly expecting some rain. So let us talk about rain in this summer. Yeah. So rainfall. Suppose we have data from a place from Pune. We have data from Pune, and we have seen, say, 50 years data. Yeah. So on an average, it rained, say, 20 milliliters in the raining season on an average, considering 50 years past data. On some years, it rained 22 milliliter. On some years, it rained, say, 15 milliliter. So like that, taking all the data, the mean of past data is 20 milliliter. And as this is a data set, it will have some standard deviation. So see, the standard deviation is 3 milliliter. Yeah. Now there is a different place, say Nagpur. So in Nagpur, we saw say a few number of years, say just this year, just this year's data we have, and we saw that say 2 years data, not 50 years, but just 2 years data we have, and the mean came out to be Pune, Nagpur, say 22 milliliter. Yeah. 22 milliliter rain fell in Nagpur. So what we will conclude, whether we get more rain in Pune or more rain in Nagpur. In other words, what we are trying to find out.
In the data, standard deviation is not given, then we have to calculate, right? That x minus x bar summation standard deviation using the standard deviation formula.
Yes, using the standard deviation formula, you have to calculate. Yeah. So in this case, what we are trying to find out is, in the language of statistics, what we are trying to find out is whether this difference in rainfall between Pune and Nagpur is significantly different or not. Or not. Yeah. So that is what we are trying to find out in the language of statistics, and this concept is called hypothesis testing. Yeah, we will define hypothesis testing in other ways also, maybe more clear ways, but this is the underlying concept. Whether this difference, here it is 20 and here it is 22, whether it is significantly different or not. It is different, yes, but whether the difference is significant or not. Yeah. So what we do is, yeah, so generally data is normally distributed. So in this case also, we assume that it is normally distributed. Yeah. So it is a normal distribution of data like this. Here is rainfall in this case. And here is the frequency or probability. Yeah. And right at the center, the mean is there. From past data, the mean is 20 milliliter. And now we have 22 milliliter. Yes. Now we have 22 milliliter, which may be somewhere here. 22 milliliter. So we want to know whether this distance is significant or not. So what it means is, if say the standard deviation is very high, yeah, and the data is varying as it is, so we can say that in Nagpur also actually the mean is 20, but just due to chance somehow we got 22. Yeah, this difference can happen by chance. Yeah. So basically our comparison in a way depends on how to what extent the data varies. The data in this data set, reference data set, varies. If it is varying too much, then we can say that this much little bit of distance can just happen by chance. Yeah. Otherwise, if we get a value somewhere here, so we will say that this much distance cannot happen by chance. It is definite that something is going on, or Pune and Nagpur are definitely different. So this much far is clear. Yeah. This, if it is this much far, then it is clear that Pune and Nagpur are different. But where to draw a line of saying that whether it is significantly different or not? So what we do is we demarcate an acceptance region and a rejection region. Okay. So usually towards the tail, we demarcate 5%. 5% of the area we keep in the right tail and 5% on the left tail. I think it has actually started raining in this area. We are talking about rainfall. Okay, let's say a rather big coincidence.
Which
Okay.
area? You are in?
There also it is raining where you are.
Here just it was few drops, but then it stopped. But
Then it stopped. Okay,
this is what.
I
Which area you
yes.
are saying?
I am staying near the Lunikalpur
Okay,
University.
yeah, yeah. Okay.
Yeah, I can smell the soil. It's nice.
Yeah, yeah.
Okay, so this area we demarcate in the two tails and we call them rejection region. Rejection region. And the area in between this area, all this area from here to here, we call it, all this area, we call it acceptance region. So when our given new value is somewhere here, here or here or here in the rejection region, we say that something has definitely changed or something has affected. Yeah, it is not same as the past data. But when our new value is also in this region, yeah, in the acceptance region, somewhere here or here, we will say that nothing has changed. Yeah. Basically, what we have represents the past data only. Yeah. So this much is clear.
Yeah.
Yeah. So uh, now our task is to find out what will be our task. What is the z value of this point? This point, which marks the 5% area towards right. What is the z value? From mean, what is this distance? What is this z value? Yeah. So how will we find that? This is called z critical. It is the critical value of z which distinguishes the acceptance and rejection region, which demarcates the acceptance and rejection region. Yeah. So we want to find the critical value. How will we find out that logically? What you will do? Yes. Think of what we did in normal distribution problems. We want 5% only towards the right. So that means
So we find out the area towards left, then we can minus it from 1, then that will be above. Is it correct?
minus it from 1. To that 5% is already given. Yeah.
Right. Right.
So what we want to know is how far is this? So we essentially want to find a z value.
Right.
Z value of this point.
Point.
This
Correct.
point. Yeah. So this point will be how much far from the mean. That is what will be the z value is. We know that this remaining portion will be how much? If the rejection region is 5%, this remaining green shaded portion will be how much?
45.
45, yeah,
Right.
or 0.45.
45.
So what is this point which will have 0.45 area under the curve. Okay, so what we know is all these values in the body of the table are areas. So we want what 0.4505, yeah, and 0.4495, both are very near to 0.45, that is 45%. So to get this much area, what is the corresponding Z value? Yeah, that we will see in this row, 1.66 and 0.04. Actually, you can take any of these two, either 0.4495 or 0.54505, and find out the corresponding Z value. That is, corresponding Z value is 1.64. Yes, 1.64. Yeah. So Z critical is equal to 1.64. Now we want to find out Z value of this new value, the new value we got. Yeah. Let us see what is the Z value of the new value. How will we find out? Z value of this new value is 22 minus the mean divided by the standard deviation, which is 3 ml. Yeah. So this is 2. Okay. So this is 2 by 3 or 0.6. 0.6.
Yeah.
Yeah. So it will go on 6. Yeah. So now what we do is we compare this. We compare the Z critical and the Z value of the new mean. We can say the new mean or the different places mean. Yeah. So this Z critical is larger than the Z value of the new mean or Z value of the new value. Yeah. So that means our new value is definitely in the acceptance region. If Z value of the new value of the variable was greater than the Z critical value, if say it was 1.7, yeah, so then we would have said that this new value is definitely in the rejection region somewhere here. Yeah. So we would have rejected the hypothesis that the new value is same as original value, same as the old value. That is, Nagpur rainfall is same as Pune rainfall. Yeah, we would have rejected that statement. Now that statement that there is no difference between old value and new value is called the null hypothesis. Yeah. So null hypothesis definition, you have understood? The statement that there is no difference between the old value, old mean, and the new value. Is it understood? The null hypothesis definition?
Yes, sir.
Okay. So what we are accepting and rejecting is basically this null hypothesis. So if our value is in the acceptance region, somewhere here or a little bit far somewhere here, so we accept the null hypothesis that there is no significant difference. Yeah. If the new value is in the acceptance region, after doing all this calculation, finding out Z critical, finding out the Z value of the new value, comparing them, if we find that the Z value of new value of the variable is less than the Z critical value, then we know that it is in the acceptance region. So we accept the null hypothesis that there is no difference. There is no difference. The difference between rainfall in Nagpur and Pune is not significant. Yeah, again, coming back to this basic concept. Yeah, if it is in the acceptance region, the difference is not significant. If it is in the rejection region, the difference is significant, and we then reject the null hypothesis. If it is in the rejection region, we reject the null hypothesis, say that something is going on. Yeah, old data is not same as new data. Something is going on. So there may be some reason. Yeah. So this is the basic of hypothesis testing. Yes. So this is what we do. I'll share the steps also. So these are the steps basically.
Okay.
Whenever we want to do hypothesis testing, this is what we do. First, we state the null hypothesis. Yeah, what is the null hypothesis? In this case, the null hypothesis will be there is no significant difference between rainfall in Pune and Nagpur. Yeah, then choose the test. Actually, there can be a couple of different types of tests, but only one test we have discussed. So this choosing part, choosing step actually is not there. Then choose the significance level. So what is meant by significance level is this 5%. Yeah. So we can choose either 5% or 2.5% in both the tails. And yeah, so those are two common choices. Sometimes we choose 10% also. Yeah. So that is the next step. Choose the significance level. Then calculate the test statistic. Test statistic means what? The Z value of this new value. Z value of 22 ml in this case. Yeah. Okay. Then the next step is get the critical value of the statistic from the table. Yeah. So there's from this table we got the critical value, which is 1.64 in our case, this value. Yeah. Now, what is the next step? Compare calculated value and critical value and interpret. Yeah. So we compared this 1.64 and 0.66, which is the Z value for 22 mm. So we saw that the Z value of new value, that is in this term, test statistic, yeah, the test statistic is less than the critical value. That is, the Z value of 22 ml is less than the Z critical value of 0.64. So we accept the null hypothesis and say that there is no significant difference between rainfall in Pune and Nagpur. So that is the interpretation. That is very important. Yeah, interpret. Yeah, many people just leave that. Hence, we reject the null hypothesis, or hence we reject the accept the null hypothesis. But what does that mean? In simple language, what does that mean? So we have to write that in interpretation. Yeah, so that is a good practice. So this is about hypothesis testing. One more important point is something called as p-value. P-value. It's getting, yeah, now black is black has become clear. Yeah. So p-value. So what is meant by p-value? What is the p-value of this 22 ml? Yeah, many times that p-value will be reported. So what is that? So p-value is probability of getting a value this much or farther than the mean. So essentially what we are talking about is, so if I'll again draw it because that has become a little congested. So this 22 is there, here it is 20 and here it is 22, here it is 22. So the p-value of 22 will be area, the probability of getting higher than 22. Yeah. So that is simply the p-value. What we have to do, we have to find out the area as we did in normal distribution in one of the last cases. So we will find out this whole area and we will subtract 1 minus this whole area. Yeah, 1 minus this whole area will give us the p-value of 22. Okay. So p-value is understood?
Yeah.
Yeah. So now let me ask you, if p-value is less, if p-value is very less, would you reject the null hypothesis or would you accept the null hypothesis?
P-value is less.
Yes, less. So when will p-value be less? When say your new value is very far, somewhere here or somewhere here, then p-value will be less. So if p-value is less, will you reject the null hypothesis or accept the null hypothesis? In this case, suppose we demarcated the area, 5% will be the significance level. Yeah, in some books it is 5%, some books it is also denoted 95%. So you have to be careful of what they are talking about. Yeah, generally it is significance level of 5%, they call it. So this portion we demarcated, so that is 5%. Yeah. Now p-value is 2.5%. So that means it is somewhere here, somewhere here. So if p-value is very less, specifically less than the significance level you have decided, then you should be accepting the null hypothesis or rejecting the null hypothesis. If the new value is too far from the old mean, we reject the null hypothesis.
Yeah.
So in this case, when p-value is less, that means the new value is very, very far. Then only p-value will be less.
Right.
Yeah. So we will reject the null hypothesis when p-value of the new value, new statistic, or the new sample's mean is very far from the old mean.
Right.
Then we will reject the null hypothesis. So that is what hypothesis testing is all about. So we did a specific type of hypothesis testing, which is comparing the mean. Yeah, and this we compared the mean. Old mean was 20, new mean was 22. Similarly, we can compare other statistics also, like standard deviation, yeah, which leads to a similar process, but in that case we do not use normal distribution. Yeah, we use F statistic and other distribution. So that is also an extension of hypothesis testing, but basically hypothesis testing is what we just discussed, comparing the means. Yeah. So this is hypothesis testing. I'll pass on this exercise. There are 2-3 problems here, and I will also share a video which explains again hypothesis testing with different examples, which definitely you will enjoy. It is a very well made video. I like the YouTube channel as well. I've been following since many years. Few very good YouTube channels, so that is one of them. So I'll pass on the link in the group, and yeah, so you can revise, and I do a little bit of practice also with this 3-4 problems. And if you get stuck, we will discuss, but perhaps we will discuss after midterm.
Yeah.
So this hypothesis testing is there in midterm. Those who were not able to join, I think
Tomorrow we have
yes,
midterm.
I mean yes, tomorrow around the same time, the present time, 9 p.m. we will have the midterm. I'll share the question paper in this kind of a Zoom meeting. Then you can write on paper, take pictures, take pics with your mobile, and put those pics together as a common PDF document. There are free software available on the internet. If you just search join documents to make combined PDF, you will get many such software. You would have done that also many times. Yeah. So prepare a combined PDF and then share. And I will check. 4 of you are there, so will not take. Yeah, so we'll be ready with the output soon, maybe in a week. Yeah. Yeah, output in the sense the marks, etc. Yes. Okay, so this completes our pre-midterm syllabus. After this, we will try to discuss some models, machine learning model. All the basic required for that is done. Yeah. Statistics, basics, mean, some measures of central tendency, measures of dispersion, then probability basics, then probability distribution. So all those we have discussed. Now we can look at some analytics portion, models, machine learning models. 4 to 5 models we will discuss. They are interesting. One of them we have already discussed. Actually, regression is also one of the models, not surprisingly. Other models are decision tree and other such models are there. Neural networks. They sound complicated maybe, but step by step we will go and we will understand the basics. We won't do complicated things.
Okay.
Yeah. So let me share this. I think it got recorded so others can see. All right, then. Best of luck for the midterm tomorrow.
Okay.
And we'll meet again Tuesday, same time, 9 p.m. actually.
Yeah.
The time we are ending, 9 p.m. to 10:30. We'll discuss.
Okay.
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 Thank you. Bye.